Okay, we're going to blast off into the world of vector calculus today. It's very interesting, so let's go. Vector calculus involves taking derivatives and antiderivatives of vectors and vector equations, guys. If you start off with the displacement or the position as a function of time, and you take the derivative, you'll get the velocity, and if you take the derivative of the velocity, you'll get the acceleration as a function of time. And vice versa, if you go from acceleration and you antiderive, you'll get velocity, and if you antiderive velocity, you will get position. These are all functions of time, by the way. Now here's an example. This is a nice easy one to kick us off. Find the velocity and the acceleration vector as functions of time if the position vector as a function of time is this beastie here. I can smell a derivative in the air, can't you? So therefore the position vector as a function of time, or the displacement, if you like, as a function of time is that. Now let's do the derivative. Therefore that is the velocity with a little dot above here. That's the notation we use. The velocity would be the derivative of this. Check whether you agree. That looks right, that looks right, that looks right. Very good. Now let's do acceleration now. We don't get anything from the I component. We just get minus 10 from the J component. And thank you, Mr. Box. Very good. Okay, that was nice and easy, wasn't it? Over to example 8. Similar, except we've got trigonometric functions here in the x and the y, okay? Same procedure though. Therefore, there's our position or displacement vector as a function of time. Take the derivative. Derivative of cos is minus sine. Derivative of sine is cos. Hence we get that. Derivative of 5t is 5. Therefore, there is our velocity vector function as a function of time. And there's the acceleration. I've just derived sine. Get cos, and cos, the derivative of cos is minus sine, so you get plus from the double negative, okay? And this doesn't give us anything because that was a constant up there. Alright, I think that's it. Thank you, Mr. Box, again. Doing a great job for us, Mr. Box, as usual. Now, what's this? We've got that. Oh, yes. Let's have a jolly good look at that. This alpha thing looks a little bit nasty, doesn't it? If you just study this a bit, guys, after getting over the initial confusion, and you think, well, hang on, alright, if I was going to get I plus j out of this position vector here, what value of t would you need in order to achieve that? Well, it seems pretty obvious after you look at it for a moment or two that t must be 1. And if t was 1 in this j component, that'd be nothing there, and you just get 1. So if t was 1, then r of 1 would be I plus j. So I think alpha is 1. That's what I'm saying, okay? Yeah, r of alpha has to be I plus j, and therefore t is 1. That's what we're saying. Now we've cracked the code. Now we just have to get the velocity and the acceleration, okay, with alpha substituted in, e.g. t is 1 substituted in. So there's the derivative of the displacement vector there. Do you agree? Good. And therefore, if we substitute 1 into that as the value of t, we're going to get that, which just gets us that, okay? That's I. Yes, my oh my. Now, here comes the acceleration now. There's the velocity function there. Here's the acceleration function, which is the derivative of the velocity. You just get this bit here from the j, because there's nothing coming out of the I, because that was a constant. No time in there. Okay, so there's that. Now we better substitute 1 into that. Okay, that's very interesting. So therefore, that's naught. Okay, that's the answer. Example 10. What's this? Oh, more alpha. Oh yeah, well we know what you're about, Mr. Alpha. We know how to crack your code now. So there's the displacement vector function, and we know that with alpha substituted in, we're supposed to get I plus j. So therefore, it seems blindingly obvious, ladies and gentlemen, that e to the t must equal 1. So we better work out, therefore, t must equal 0. Of course, there you go. And therefore, the velocity vector function equals, I've just derived this thing here. That's what I've done to get that, yeah? And what I'm going to do is I'm going to substitute 1 into that. I'm going to substitute naught into it, not 1. I'm fixated on the last question. So t is naught, yes? T is naught up here. So therefore, the velocity at naught would be, this would be e to the naught, which would be 1, and all of this, What would that be? E to the naught is 1. 1 minus 1 is nothing. Therefore, that's just a nothing. Yes? So there it is. It's just I. Hi, I. My, oh my. So now we better move on to acceleration, better we, guys? So I'm just expanding out. In that line there, I've just expanded out this quadratic-y looking things here in preparation for taking its derivative, okay? So, and cleaned it up so it looks a bit nicer. So therefore, what does that equal? Yes, a little bit more cleaning up of this. Now we're going to hit it with the old derivative trick, and we're going to get the r double dot, the acceleration vector function, is this. Now, that's the derivative of this, that's right. This is the derivative of that, and that doesn't change, does it? No. Okay, so now we can substitute naught in there, and there we go. Does that look right? Well, let's see. E to the naught is 1, that's going to be 9, that's going to be 12, and that's going to be, yeah, very easy, very good. So that's going to be 933. Oh, we're going to get a 0j component. Again, just I. My, oh my, I. So there you go. Example 11, guys, we're burning it up. A curve is described by the vector equation RT equals 2 cos t plus 3 sin t. Okay, I is the cos and j is the sine thingy. Find that and that. Well, I don't see a problem with that, do you? Not at all. Find the gradient of the curve at the point x and y, where x is this, which just restates that, and y is that. Yeah, well, this is a pretty easy question, guys. I can sniff some chain rule in part B. Did you pick that up? So A part 1, right, here we go. R of t, that's the position vector function, is that. Therefore, we're going to derive that and get the velocity. Have a look. Do you agree? Yes, I think so. That's good, and that's the answer to that one. So now we'll do A part 2, the acceleration. We're just going to take the derivative of this one now to get the acceleration vector function. There it is. There it is, yes. Derivative of sine is cos. Derivative of cos is minus sine, hence the minus 3 sine t. I think we need another box. Thank you, Mr. Box. Now, what are we going to do now? We've got to do part B. Alright, now we've got to get the gradient of the curve. Now, I said chain rule, didn't I? Yes? Well, let's just see. Let's just see. Rather than scratch your head and think, oh my goodness, what am I going to do here? Just feast your beaties upon this, guys. Look, dy dx equals dy dt times dt dx, and we've already got these beasties up here. See, look, x is this and y is this. So we can get dy dx, but it'll be in terms of t. How interesting, you see. There you go, there's x and y, there's dx dt, minus 2 sine t, therefore dt dx would be the reciprocal of that. That's taken care of that bit. See, I'm heading up to the chain rule here, see? Yeah, now we've got to do dy dt now. Dy dt is 3 cos t, therefore dy dx will be dy dt times dt dx, and there it is. There's your answer. I've just made it look a bit prettier by calling upside down sine over cos tan. So tan's on the denominator. So that's your answer. But the dy dx is in terms of t. There's nothing wrong with that. They didn't say how they wanted it expressed, in which variable they wanted it expressed in terms of, so we're right. Okay? Very, very excellent. Now, what I've just added a little PS there is that if tan t was naught, of course we'd be in serious trouble, wouldn't we? And dy dx would be undefined. But you don't have to say that. You don't have to say that. I'm just saying it for the point of completion and completeness. Right, example 12. A curve is described by the vector equation, that beastie. A second of tan, that's a hyperbola, guys. I can tell you that. But we won't have to work that out in terms of a Cartesian situation. Find the gradient of the curve at x and y, where x is that, yeah, okay, same thing. Same thing. Oh, except we have to substitute the value t as pi on 4 into it. Yeah, that's all right. No problem. So we've got this position vector function is this, and we're going to say that therefore x is that and y is that. Now let's do dx dt and dy dt. So x is that, dx dt will be, goodness, a bit of chain rule there. Very nice. So what does that come out to be? Goodness me. Yes, sine t over cos squared t. Good, that's dx dt for you and me, and therefore dt dx will be the reciprocal of that. Okay, now we'll do the same thing with y. We'll get dy dt, that'll be sec squared t. Now, we're set up now, 1 over cos squared t, therefore, dy dx is dy dt times dt dx by the chain rule, And what are we going to get out of this? It's very exciting. Look, those coses are going to cancel out. Good gracious. And we're just going to get cosec t. Cosec t for you and me. And now we can substitute in our magic number here. T is pi on 4. Now, you've got to think, what's sine of pi on 4? It's 1 over root 2, isn't it? Therefore, cosec of pi on 4 would be the reciprocal of that, which would be root 2 over 1. Root 2 over 1, I predict. Yes, excellento, excellento. We've done it. You see? We're flying high, my oh my. Now, what's this thing? Oh, we're starting off with the acceleration here, and we've got to find the velocity given a boundary condition, and then from there to find the displacement given another boundary condition. So this is the same old, except we're anti-diffing. We're anti-diffing this time. So, okay, let's go with it. There's A. There it is. Now we're going to anti-diff that. Have a look. And notice how I've written vector c as my constant. That's a perfectly valid and very efficient way of doing it, guys. So we're going to put our boundary conditions in now. They told us that r dot 0 was this, so we're putting that in, and we're working out what vector c, constant vector c is. There it is. It looks like it's all of that left-hand side. Great. Therefore, I've put it all in one great big thingo there for you with that's the velocity vector. Now I've put the 10t in with the I component of c, which is this 30, okay, and then there was, what do we got here? There's the 12, oh yeah, there's no j components in terms of t up here, so I'm just putting in the minus 20j here from the constant bit, and I've got minus 10t plus 10. There's that 10, and there's the minus 12t in the k. Yeah, and thank you, Mr. Box. So that's the velocity vector function. All right? Now, what are we going to do now? We're going to do the next bit. We're going to anti-diff that now and get the displacement vector function. So off we go, blast off. See what you predict. What do you think? What are we going to get for the I component? Yes? Do you get 5t squared plus 30t? Very good. For the j component, minus 20t. For this one, it's minus 6t squared plus 10t. Very good. Plus another vector constant, which we'll call vector d. Vector d. Now we'll put some boundary conditions in, because they told us up here that naught was that. Right, so we're putting that in on the left-hand side. And that equals, with the naught substituted in, we're just going to get d is equal to, I think, this. Yes, very good. 2k. Today, hooray. Now, we can then finish it off by saying that RT equals all of what we got before, but with a 2k added into the k agglomeration over here. Okay? That looks like the answer. Yeah, Mr. Box. You're beauty, Mr. Box. Okay? Are you happy with it? It's pretty straightforward, isn't it, really, this vector calculus, just doing straight old calculus on vector functions. Now, I think this might be our last one. Acceleration again. Oh, yeah, minus 9.8j. This is our displacement boundary conditions. This is our velocity boundary conditions. Same old, same old. Let's go for it, guys. There's acceleration vector function. Taking the anti-diff of that, we would get that, wouldn't we? Yeah, and here's our little constant here. And we're going to put our boundary conditions in. There they are on the left-hand side, and that equals the right-hand side with 0 substituted in for t. And therefore, we're just going to get c equals all of that left-hand side, aren't we? Therefore, here it comes. R dot t is this from the I. Is that right? Yeah, that's right. Yes, because there was no I component in terms of t from the anti-diffing up here. So just 30i, which comes from our boundary condition. Then you've got the minus 9.8t plus 40 in the j, the 40 from the boundary condition, this bit from the anti-diffing up there. So there's our velocity vector function, right? Now, here we go, another anti-diff. There you get 30t out of that. You get minus 4.9t squared from this baby. You get 40t from this guy, and then you've got, of course, good old vector constant d, which we've got to work out, don't we? Yes, R naught is naught. Okay, R naught is naught. Boundary condition, therefore we get all that, therefore D is 0. Okay, and therefore, there it is. There it is in all its glory, okay? You've got it, haven't you? The displacement vector function is that plus that. Yes? You're right? Yes, and you're a star, of course. You're a star. Huzzah, huzzah, and hurrah. And that's the end of the little video on vector calculus. Yes? And one more to go, and then that's the end of the entire blooming course. Okay? Isn't that incredible? So thank you for coming to be with me today. Have a wonderful day, and we'll see you for the grand finale.